the idea is to show you what you can do with Postgres without having extra stuff. So basically we have 4 topics here. I don't see anything, so I will zoom this if I need to. We will just say, okay, let's find substrings. Very simple, very, very technical, very programmer-like. I have a huge number of text. I want to find occurrences of substrings. Then there's full text search. How is this different? Why is full text much more than just looking for substrings? Fuzzy string matching. This is just very short. I did not know a lot to talk about this, but I put it there so it's complete. And finally, what now everybody finds cool, it's this semantic search with embedding vectors. Okay, so I have a demo set up. If you are old, you remember that I did already a talk where I showed full text search in Postgres, on the corpus of Wikipedia. I did this again. I took again Wikipedia and parsed the titles and the articles from the German, the Italian, and the English-speaking Wikipedias. So we have a lot of stuff here. We have 7.1 million articles in the English Wikipedia, some less in the German and Italian one. This is overly here. We have, for the English Wikipedia, we have 27 billion characters, so that's a lot of text. You won't have that much text typically, so if the message is also if it works for this amount of text, it will work for your amount of text as well. Here are some stats, just out of curiosity. You see the tables in Postgres are very small compared to the characters because they are compressed. So Postgres stores this data in a compressed way as well. This helps a little bit. And yeah, that's it. Out of curiosity, you see here the statistics about the length of the titles. If you ever wanted to know what the longest title is in Wikipedia, that's in the German Wikipedia, fulfilling the cliches. It's a federal law in Germany. You can click on the link to see the title of the law. Okay. The nice thing about German law is that they always have these cool abbreviations. So there is, where is it? It's the Solltreha Homge. So they make these long laws and then they shorten them up. Okay, so yeah, 2 words about this the installation I have here. I did everything. There's also timings and benchmark. I did everything on this VM, which is a modest VM. I did not trick you by booking a very large machine. This is 16 gigabytes of RAM and 4 threads, which you never know if it's 4 core or just 2 cores with 4 threads because the cloud people trick you. But anyway, it's a modest machine. It's less powerful than this notebook, for example. Okay, so yeah, there's some configurations here. I think it's not so important. All the timings you see here, I will show off very good timing measurements here, of course. And all the timings were done with a warm cache. So I repeated the query so that the index data structure is loaded into RAM, and you see effectively what Postgres has to compute and not the disk I/O. Of course, if you boot the server fresh and do a query that needs to load gigabytes of index first, then this will be naturally slow because it will need to transfer from disk. Postgres does, however, never cache query results, so it's not cheating. If it cached the query results, matching the query and say, I did this, here's the result again, that would be cheating. It's not the case. So, yeah, we have these 4 things. Let's start with the most simple thing. We want to search for substrings. Now, the use case is for whatever reason you want to look for substrings. I have here an example. This is very advanced. I can copy and paste here. This is something cool. And you see this is, for example, a query that just searches with a where clause, where title, I like South Tyrol. So this is a typical SQL substring merge where you have these percentage signs that are the wildcards of like. And in Postgres, as Postgres texts are case sensitive, so you have to say I like to ignore the case. And yeah, it's just that. We want to find all the things that, all the titles that contain South Tyrol. So if we do this, we find that this is fast. Okay, here is very fast, but here is, what does it say? It takes 1.3 seconds. Not here because I already made the index, so this spoils everything. But if you do this from start, I can, when I share the material, I will give you a link where you can download the naked tables if you like to, and then do everything I did here to create indexes and so on. So this takes 1.3 seconds, which is not bad. I mean, it's 7 million strings that are up to 200 characters long. It's okay. I mean, it does like searching substrings at a rate of, what is this, like 5 million per second or so. It's not bad. But of course, we can do better. Now, how do you do this? You probably know indexes from databases, the standard B-tree indexes, which order the data. They work a bit like a textbook. You order the data, then you have your data ordered, and then you look in the middle and say, no, I have to go left or right, and this way you eliminate half of the possibilities at each step, so you get this log n behavior, and you can quickly search everything. This does not work if the query wants a substring that has a wildcard to the left and to the right. It does just not work, okay? So here you need to get into the toolbox from computer science, looking at the university, and we need two tricks here. Okay, so the motto is Postgres can index anything. Let's see how we can index this. One trick is trigrams. Trigrams is a technique to split a string in sequences of up to, well, exactly 3 characters. That's why they're called trigram. But there's also single trigrams that have spaces at the end and the beginning. So it's actually, it looks like it's just 1 character, but it's always 3. So for example, if you use this function show trigram of Postgres, you can show what the trigrams of South Tyrol are. Here they are not ordered, so it looks a little bit messy, but you will see that any combination of 3 characters in that string is there. So this is a set. We're talking about sets, Mengen. The second trick is Postgres has an index algorithm that is called GIN, stands for Generalized Inverted Index, that can index, search, or filter operations where you look for sets that are contained in other sets. So it can speed up subset searches. How it does this is some computer sciencey thing, but it works pretty well. So we are combining these two things. We split our, or when we create this index, we are going to split the strings in trigrams, and then we build a GIN index on them, so we can speed up searches that look for the word we are searching for in the larger subsets that we pre-computed by doing the index. This sounds very complicated, but it's very simple. The statement is just this. You create an index, nothing special here, create an index, but you say using GIN. The default is that you don't say anything, then it's a B-tree index, and here you say using GIN, so it uses the GIN index. You say the field, this is standard syntax, you probably know, and then you put something that is Postgres specific, you say which operator class. So you tell it, okay, use the GIN algorithm, but the implementation, that's called GIN trigram ops. So the one that works on trigrams. Postgres has kind of two things you need to define if you do an index. You have to say what algorithm with using, that's GIN, and then you have to say what operator classes, so what data types this is implemented on and what operators it works for. So we want this for trigram operators. Okay, that's it. This is rather quickly. It does not take long to create this. The index is not even that large. Can have a look. Of course, this is now all too, this is so zoomed that nothing is fitting there. So which one is this? Let me see. I don't find it. Because it's on all three of them. So this is the NWiki title X, this one. This is 399 megabytes, so not even that large. And what does this do? This speeds it up tremendously. If I repeat the query, and I did already show you, so I spoiled it, not this one, but the one that looks for South Tyrol, you will see that this finds the 68 hits here in just milliseconds. Okay, so this is 100 times faster. Before it was 1.3 seconds, now it's 10 milliseconds, it's 100 times. If you buy a larger computer, you don't get 100 times speed up. So computer science beats hardware engineering. It's very important, this thing. And of course, the trick is that people don't know that Postgres has all these special indexes, don't do these indexes, then have slow performance and think they need to install whatever, Elasticsearch, so I don't name names. And the trick is you just have to know the tools you have inside Postgres, then you don't need something else. So this is very quick. Now, people say, yeah, but I want JSON, etc., etc. That's no problem, because you can build the same index by specifying here an expression instead of a field. Postgres has indexes on expressions also. So just make your big table with just one JSON field. You have the classical semi-structured database looking at Rudy. And just make this index on the expression that selects the field that contains your substring. Then if you put that in the where clause, it will use the index and you get the same speed. So it's not limited. The nice thing in Postgres is that everything works together. It's not that, yes, we have JSON, yes, we have gene indexes on trigrams, but you can't combine them. In Postgres, if there's a feature, you can combine it with everything else. This is an important point. There's a lot of stuff that has been submitted as patches to Postgres that has not been permitted into Postgres because it is just not flexible enough. So, do you like regular expressions? Do you like regular expressions? Yes, you do. You're all nerds. I know you. So, this thing here speeds up regular expressions. Sorry?
No Perl program was in the crowd.
No Perl, yeah, but regular expressions are, in the meantime, they are everywhere. So if we want to formulate this as a regular expression, you can use the tilde operator, which is a regular expression in Postgres, or the tilde asterisk operator, which is the case-insensitive regular expression. You can put a regular expression there. For example, let's look for, I don't know, we could look for Tyrol spelled in two different ways. So write it as Tyrol or Tirol. Let's see what this gives us. So this is a regular expression. Don't know if you know the syntax, probably you do, that says I want to search all things that contain Tyrol or Tirol. Okay, so yeah. Look at this. This finds a lot of data now. Well, not even, 392. And the speed is here also in the millisecond range. So it's not just I like, it's regular expressions as well. There are 7 million titles here. Okay, so that already kills it. You just use the gene index on the trigram operator class, and you can do I-like and regular expressions in milliseconds. This is not scaling linearly. This is scaling better than linearly. So if you have even more, it does not take n times as much time because it's still a kind of logarithmic behavior there. So basically, you can do everything in milliseconds. Of course, the index needs to be warm. I always treat with clients that have these databases with like 0.5 terabyte of indexes, not naming names. And then they have that running on machines with 4 gigabytes of RAM. So what happens is that the last user that used something will have a good performance, and everything else is on disk and needs to be loaded again. Now, let's move on to the bit more complex thing, full text search. Okay, so to be not too abstract, I have these nice use cases. So we have natural language documents, not just the titles, not just strings, but we have longer documents, like the Wikipedia articles. And we want to give query terms and find all the documents that have these query terms. And then we optionally, or most of the times we need this, we also want to rank them, especially if the search term is not very selective and we find 1,000 hits, we want to rank them. So this is done by full text search. Full text search is built in Postgres since forever, basically. It's not something new, it's not an extension, it's just built in since the dawn of times. Let's talk about what is a document. A document here means some text. Of course, it can't be a binary document. You need to have the text in text format, but it can be quite long. A text typed on a typewriter is 2,000 characters per page. So the Wikipedia article here is a nice corpus. We have 47% of all articles that are longer than 1 page. 8% are longer than 5 pages. So they are not just strings, but let's call them documents. Now, we could use, do a trigram, a gene and a trigram, a gene index with trigram operators on this. We can do this and then use like. Why not? It works. I did it for you just out of curiosity. To find the 3,038 article bodies that match South Tyrol within with this index. Without the index, it takes 75 seconds here. With the index, it goes down to 3 seconds, which is a lot, which is already quite impressive. But it's not good enough, because the goal should always be to be able to search things in milliseconds, in tens of milliseconds. And furthermore, there's besides performance, there are other problems here. There's also problems of linguistic support. If you do I-like, there's no information about word boundaries. An I-like will find you a car in an article that talks about carpets, because it has no concept of word. Huh? So another thing is that maybe you're looking for a car, and in the article there's just the word cars. So it's not even that simple that you can just split the words. You need to have some linguistic, some lexical information and knowledge about the language you're doing. Then there are stop words. You don't want to put the or a in that index, because that's very likely in all the documents, so it does not help at all. Finally, ranking. If you do like, you get a Boolean back. True, the substring is there. If it's there, you could even somehow find where it is, but yeah, how do you rank that? There's no way to rank the documents. So to solve all these problems, people came up with full text search. Full text search in Postgres uses a data type that is called a TS vector. TS stands for text search vector. And there is a 2TS vector function that shows you how such a TS vector looks like. For example, I have here the sentence, a computer is a machine that can blah blah. Some sentence, this is from a Wikipedia article, of course. And if I apply to TS vector to that one, it will get you something like this. So this is interesting. Look at what it did. First of all, the stop words are not there anymore. Is there a the, or, of, is all not there. Then you see that the words have been stemmed. So programmed, which is some kind of past, has become program. Okay, and yeah, auto, where is it? Automatically is just automat, so it's stemmed. And then you see there is information about the positions. This is the position. Compute appears as word 2 and word 20. Actually, it's here, word 2, and this is word 20. It's not even the same word, but it's the same stem, compute. So if you're looking for something like computers, the system will be able to tell you, it appears here twice. Okay, so that's the TS vector. It's explained here. Stop words, stemming, and then the position. Now, Postgres supports 29 languages. What you see here is English. That's the default because there's a configuration that defaults to English. But you can do this in any language, or any of these 29 languages, like D, F. Here you can see them. Here they are. Italian and German is there. There's also simple. Simple will be useful later. Simple does not do any stemming, any stuff. It's an empty language. So there's no rules. It creates a text vector that has exactly the words as in the original text. So here it shows the same text from the German Wikipedia article. You see here I just give German. Of course you can also configure this, the settings, and then German will be the default. And here I also have Italian. Oh, I already forgot that I have this copy feature. Okay, this is the Italian one. So we have this. We have this TS vector. Good. That's a basis. Now, ideally, I want to pre-compute these TS vectors. I don't need to. I can do full text search without pre-computing them, but if I pre-compute them, I have a few advantages. We see later which ones. So I want to compute them. Now, you don't have to do complicated stuff like doing other tables and triggers and so on. Postgres has a nice feature that is called generated columns. You can just say alter table and wiki add column, I called it FTS for full text search, is a type TS vector, and you have this syntax here, generated always as, and then you give an expression. So this is a kind of system to have a materialized column calculated from the other columns, and this will be always up to date. It is like an auto-refreshing materialized column. This is very handy. When I did this talk 7 years ago in Trento, this feature was not there. You had to do triggers to do this. Now, this is very handy. I did this, and I computed these generated columns. This took some time, 44 minutes for the English Wikipedia, so it's not easy. This is the articles, so the 27 billion characters, so it's not just the title. The title would be very quick. This is really the articles. And a bit less for the other wikis here, 20 minutes, 10 minutes. Okay, so, how do we search? We have now these TS vectors. We even did materialize them. How do I search? There is also a TS query, a text search query. That is a data type that defines your query terms. There is some syntax here. You need to have the query terms, and you have these operators. This means and, or, not, and this means followed by. So if I want to search South Tyrol, I have to give it like this. Select South, and this arrow Tyrol. I can also put this into 2 TS vector, and it will stem it and everything while there's no stemming happening here. Probably this dictionary is a bit simple. It probably does not know what Tirol is. It can't stem Tirol, so it just leaves it like this. Okay, so this is my query. Now, Postgres has an operator that combines these two. Ah, no, I have to say, okay, sorry. There's another thing here about German. So I have another example here. You can do the same with as you did with ds vector in other languages. If you put German there and give die Bäume, it will become Baum because die is a stop word, and Bäume gets correctly, surprisingly, stamped to Baum, which is correct. So in this case it works, but the stemmer is not really 100% perfect, but you don't need 100% perfect most of the time. Okay, so how do we search things? We search things with this operator. Postgres has this infinite amount of funny operators that you don't know existed. This is the operator that takes, it's symmetric, so you can have query, ts vector, or ts vector, ts query, does not matter, and it will return true or false, whether it matches or not. So you apply this to our pre-computed column FTS. Here we go. How long did I say that this will take? Okay, so these are the, this is not exactly what you see with iLike. Okay, this is a lot. Oh yeah, this is the 2,700 instances. Why are they more than 68? Because these are the articles. So, of course, there are more that contain the term South Tyrol. Why are they not 3,000? Because they are less than iLike, because iLike also finds other pieces like Tyrolean, etc., that has not been stamped correctly in this case, so it finds a few less. Anyway, this works. This is not super fast. If you do this repeatedly in a few times without an index. So here I already have the index, but I did it before I had it. This will take 90 seconds. So that's quite slow again. It's actually a little bit slower than iLike. iLike was 75 seconds, if you remember. And then with the index, we brought it down to 3. This starts at 90, so it's even a bit more slow than iLike. Now, the drill is Postgres can index anything. Let's index this one. Again, in this case, since this ts vector is also a set. It's called vector, but actually it's more like a set because the ordering of the words does not matter. So whenever you search subsets in sets, the trick is to use this gin index. So here we can use the gin index using gin. But we don't have to say anything because gin already understands that FTS is a TS vector field, so it knows what to do. It already automatically finds the right operator class. Just say this. Now this also takes some time. Again, a little bit in the same order as creating the TS vectors, but if you have these indexes, now this query is very fast. Here it took 3 seconds because it's I did use other stuff, so these indexes were back on disk. If I repeat this a few times, I get here a very good performance. You see I go down to 35 seconds, 35 seconds, 34 seconds, milliseconds of course, 35 milliseconds, 35 milliseconds. So you're back there. This goes down to, I think I put it here, 40 milliseconds. Yeah, so now we see 35 even. Okay? So that's spectacular. We went from 90 seconds to 35 milliseconds. Okay? So that's 3,000 times faster due to these gene indexes. So now, yeah, you can do full text search. What you want to find? We have 3 Wikipedias here. Tell me something. Clemens, you're eager to tell me an example.
I wanted to find full text search.
In which Wikipedia? In the English one, okay. So let's look for full, followed by text, followed by search, like this. Takes an awful amount of time. We really have to warm this all up. We have to do a few searches to get this all into RAM. Okay, here we are. Oh, it finds own cloud. Interesting. Einheitsübersetzung. Was ist die English Wikipedia? Yeah. Why is Einheitsübersetzung in the English Wikipedia?
Because it's probably a lower one, like Zeitgeist.
Ah, do they have this Einheitsübersetzung? Yeah. It's a word in English, apparently. Okay. And yeah, that's a good question. That's a very good question. So English, Einheitsübersetzung, full. Oh yeah, easy full text searches. Yeah, you see, even the here you have a plural, still found it. So stemming in this case worked. Okay, very cool. Now, first time was a bit slow. Now it's getting faster. 133 milliseconds. This is also quite some matches, 277. The point is, this index is, because I did different things here. The last thing I did this afternoon was with the last part, with the semantic search. So these indexes are not fully loaded yet. For example, this NWiki FTSX here is 6 GB. If you do different searches, at one point, this 6 GB all the pages will be in RAM, and then everything will uniformly be quick. So you have this very strong warming effect here that you take into account. Something else, you can also not do the close to, but you, like or end or Patrick. You want to search for Neue Tech Park. Okay, that's another one with the close to. Okay, this was quick. 9 hits in the English Wikipedia. So everybody is asking who this guy is. Does anybody know this guy? No? So let's have a look. I prepared here. This is, by the way, the copy fail bug that I had bookmarked for good reasons. Okay, so let's see where tech. Yeah, here it is, Neue Tech Park. Okay, who's this guy? This guy is a conceptual artist. Okay. Okay, something else?
What about Open Data Hub?
How do you, is this one word or? Yeah, I don't think this is in Wiki.
Someone wrote in the description.
Okay. Florida State Road 563. Okay, that's interesting. We absolutely have to check this out, right? Open data. Oh. F.Open Data Hub. ArcGIS. ArcGIS. Okay, it's a map, kind of map. Okay. So you see it really works. Of course, this is all now very quick if you repeat it because the pages are there. Something with and or not, or let's not do always this followed by something else. Be creative. Can also be another language. Pick German. What do you want to find in the German Wikipedia?
What was the question? And or?
Yeah, do something with and or. So you want to find everything that talks about Kakteen and Mühlen, but not Büroklammern.
Let's try it. Kakteen und Orchidee.
Cactus. Oder, no, I don't know if the stemming will work. Kakteen. German. Kakteen und Orchideen. Okay. Yeah, it finds 79. Okay. Let's see if the stemming works here for Cacteen. I don't know. I can do a 2ds. Well, I can copy this. Select 2ds query. Cactee. Und cactus, this is not completely correct, and cactus is cactus. So here the stemmer does not know the irregular, it thinks that cactean is the plural of cactee, which makes sense if you don't know that it's an exception, right? So here, for example, this query did actually find just pages that have cactean, or any word that stems to cactee. So possibly it's not complete in that sense. As I said, stemming is a little bit a weak link here. Okay, I guess this works. And let's add...
Let's do cactus.
And what cactus?
No, if you change the search because you left Kakteen.
Yeah. If I change to cactus, it actually finds less. Look at this. I wanted to try think something else. Cactean and orchidean and not Rohr cactus. What cactus? Rohr. Ah, oh.
Put it in brand.
Ah, okay. Yeah. Cactus or cactean and orchidean. So yeah, that's a nice grouping. Perfect. We have 84 here. Okay. How many did we have for just cactean alone? Didn't we have more with just cactean alone? Ah, no, 79. Okay, 79. And with cactus or we have 84. Okay. Yeah. But normally you don't need to do this because stemming will take care. This is just because it's an unfortunate plural here. Okay. So yeah, you can do this. And if I continue doing this, it will get quicker and quicker. Let's look for PostgreSQL. Okay. And at some point, everything will be quick because this 6 GB will be completely cached. Great, that's full text search. Now, one problem is that if you do here, you see, if it's very selective, it goes even down. If you have the fewer results you have, the quicker it is. And for example, this is the query I did in Trento some years ago, and this is quite selective. And this goes even down to single-digit milliseconds if you repeat it. It's a combination of strange words, and apparently you have articles, especially this list of articles in Wikipedia have everything. Okay, very cool. So there's one problem here. Okay, so here I mentioned this is a detail. If you, later you want to follow this, there's a trick. You can do these expressions here as well, and then you save space. But now let's consider a problem. Let's do again the query with South Tyrol. It's actually pronounced query, but I somehow always call it query. So where's the South Tyrol here? I think it was at the top, right? I can't find it anymore. Here it is. No, this is not the query. Where is the South Tyrol one? Here it is, yeah. Okay. So if you do this again, there's a problem here. The problem is that you get a lot of articles, which often happens, like 2,700 if I remember correctly, but these articles are not ordered by any meaningful thing. They are basically random here. There's no order by, so they are random. And as chance wants, the first is about this Turopolje, which is probably a nice animal. I think I even linked it. Let's go down to... yeah, I don't see anything. It's just so small for me. Okay, so I linked it. This is the Turopolje. Of course, I checked that the South Tyrol is there. It is. Here it is. But it is certainly not a good first place. Okay, so if you redo this database, maybe it is even something else. So the problem is now we need to rank this. Now, if you have metadata, you could add an order by recent documents. Yeah, if it's your documents, probably you have the author, you have the date, you can rank them by recency, you can do all kinds of things. Maybe you monitor how many times they are requested, so you have good ordering criteria. But suppose you don't have anything. Suppose you have just the naked documents, like we have here. How do you rank them? Now, there is actually a thing that's called the cover density ranking, which works this way. You look at how many times the word occur in the document, and well, in the case that you use the follow operator, it doesn't matter, but if you don't have a follow-up, you also want the two search terms be close together. So you don't want a long article where there's South and Tyrol somewhere, but not South Tyrol. So you can compute this thing here, which is a standard algorithm. Online there is a lot of kind of voodoo talk about these ranking things. Basically, this is not something new. This was computer science people solved this sort of in the 80s and in the 90s. So sometimes there's a blogger that discovers an algorithm from the 80s and thinks he or she has found something new, but it's basically old stuff. This has been in Postgres since a long time. I went back to the manual to see if this is something new, because at some point everybody started to talk about this ranking. I said, is this new? And I found that it's in Postgres since forever. How does this work? You do your query. So this is the same where clause here, as always. But you add in the select list a call to this tsrank cd. And you have to give it the column and the query, because it needs to know the query, because it needs to calculate this for your specific query. You can't cache this. It has to be recalculated. Now, if you put it in the select list, Postgres will call this only for the records where the where clause matches. And this is a well-known problem. If you have if you search something and you get 1 million hits back, this would mean that you have to call this ranking function for 1 million records, which is not good. So later I will go back to this. You have to be a little bit attention. You should just rank with this one if you know you have a limit somehow. You can just do a query without ranking with a limit 1,000, and if you see you have 1,000, then you have to step back and say, oops, wait a second, I have lots of hit, and maybe change strategy. Maybe you say this is a common word, let's maybe just look at the titles. So to avoid to have something. I played a little bit with the search on Wikipedia. I don't know how they do it, but I think they do it similarly. If you search a very common word, it feels like they just look in the titles, which is reasonable. So, okay, for South Tyrol, this is not a problem. 3,000 rankings can be computed quickly. And this is the query. These are two versions here. The first one is a little bit ugly because you have to repeat your 2TS query, your query is repeated here, so this is a little bit ugly. But with Postgres, you have also this with syntax, or it's not a Postgres thing, it's a standard SQL things. These are common table expressions, and you can define basically you create a temporary table with just this one column and one row. So you do this once, call this my search, and in the query then you refer to my search. You just join it here. So this is, it's not really a join, it's just a join with a table with one row. So the row is just copied over there. And this way you have, you can call it here, and you can put it just once and edit the text just here in the first line, and it's a little bit easier to play around with, but a bit harder to understand maybe. So if you do this, wow, the peak is now down. I checked it out. It's at 57%. It's somehow in the around the middle. And we get a very good ranking. Look at this, very beautiful. South Tyrol, Bolzano. Okay, then we get Italian cheeses for some reason. It probably is because South Tyrol has quite a number of cheeses. So I can imagine that in the long list there are a few South Tyrols. And yeah, you get stuff that is somehow very related to what you're looking for. This is about the best you can do if you don't have any information. People come to me and say, yeah, but Google, yeah, okay, Google knows everything about you. If you look for a restaurant in Google, because you want to eat a pizza over there, you give the name of that pizzeria, Google will give you the opening hours for this pizzeria, because Google knows who you are, where you are, what you do. If I search the name of this pizzeria here, given that it has a Wikipedia page, there's no information, no such information. So yeah, it is poorly constructed from the text corpus alone, and for this is very good. To be honest, stemming is a bit weak, but ranking is very good. If you see all these blog entries of people that come up with these phantomatic new ranking algorithms, I really don't buy into this. I think this is really well done. Old stuff, 90s stuff. Okay, so very good. This is the note about this limit thing. Pay attention. Don't compute the coverage density for millions of results, because it's going to be slow. This gives a little bit of a problem if you want to rank. One of you had this problem once a few years ago. If you want to really rank lots of things, this function is maybe a bit too costly. But for search, you don't usually need to, because you always have some kind of filtering. Okay, I think I'm not taking too much time. I'm still on track to finish at 20. Of course, there's questions and experiments. Just interrupt me. The third of our four parts here is fuzzy string matching. I didn't do a lot about this. This is also quite interesting. The idea is that you do something like substring searching, like we did with iLike, but you want to do it in a fuzzy way. And one use case might be to offer possible corrections of misspelled words. If you go into a search engine, you know there are these suggestions, and they correct your word. They ask you, did you mean something else? So how could you do this, and how could you do this fast? Now, first of all, here there's some useless things to get a list of words, because we want to do this on words. Okay, of course you can say I want to do fuzzy string matching in documents, but the more popular thing is that you want to do it in words, because you use it to suggest corrections of misspelled things. So here's a small trick. I will not go into this, but if you do exactly this, you have a very easy query that generates you a table of distinct words from another corpus. So you don't have to program this in Python or something. You can just do these queries and you will get a nice word list. Here it is. I called it N words, D words, and ID words. Have a look. select star from n words, limit 10. So these are, okay, yeah. Wikipedia, of course, has also, strange things. Let's do,
The German one's different.
let's do, we can do this. Table sample, yeah, that was also, but this is cooler. This gives you a random sampling with the given percentage of data from the table. Okay, so this is the, but it's not the same number because for each record it evaluates that random property, so it's not always the same number. You see, these are single words, and they are unique. So Italian. Oh, Italian has Wattenbeck. That's very Italian. Okay. And English, let's do English as well. So we have this singular word. Of course, this is a bit of a strange word list. Maybe you want to use userdict from Linux. Linux has a file that is, I think, usershare-dict or something that is just a word list. You don't know this. They used, for example, they use this if you want that your password is not a simple word or so. They use these word lists. Maybe this is better because these are real words. Wikipedia is so strange; they have kind of really weird things there. So maybe don't use this, but use a simpler word list from n words. Okay, so yeah, you see this is a lot. There are not 1.9 million words in English language. This is all kind of weird things that Wikipedia knows. Okay, so this is the first step. I will not go into how I did this. It's just a simple trick that you can use. Now, the point is now we want to give, our search term is now something that is spelled correctly or not. We don't know. Maybe it's already present in the word list or maybe not. And I choose as an example Postgres. This is a common error. Postgres is not an accepted name for the database system. As you know, the database system is called PostgreSQL or Postgres, but never Postgres. So Postgres is wrong. And I want to check out if I can find possible corrections for this word. Now, one thing we know from computer science is that there is a concept called edit distance, which counts how many insert, deletes, and substitutions you have to type into some word to get another word. Okay, so in this case, the edit distance is 1. You have to add one S, then it's good. Insert one S, it's good. Now, this is commonly used an implementation of the algorithm by somebody called Levenstein. It's a well-known thing. Postgres can do this. It has a Levenstein function. And you could just say, well, very nice. I did this again with this with thing here, so I don't have to repeat the word, because I used the word twice here. Well, in this query, I used it once, but later I use it twice, so I don't want to repeat it. I use the with syntax, but I don't care if you repeat it. If you do this, you already get the result here. So basically, we could go on to semantic search finally. But the challenge here is also to speed this up. This is actually quite fast. But yeah, it is a kind of, we have these itchy fingers that we say we want to bring this down to milliseconds as well. Well, it is milliseconds, but 100. So that's quite a lot. Now, does this work? Yeah, sort of it works. You see here we have 3 candidates that have an edit distance of 1. One is Postgres, which is just adding a 1. One is posture, which changes a U with a G. So substitution is just counting as 1. If I substitute a U with a G, I get Postgres here. And this is, I add a G. So, yeah, these are.
Postgres, why is Postgres not 0? Sorry, I don't understand.
We are looking for Postgres.
You are looking.
Yeah, I gave the misspelled word. Of course, the word does not need to be misspelled. For example, if a user here enters Postgres, you will find, oh, I have a 0. So, yeah, okay, you can do this secretly, and if it's 0, you say, very well, I will look for this word. So, back to Postgres. So, we have these 3 candidates, and this sort of works, but is, yeah, not super fast. Well, if you do exactly this, there's a small trick. Postgres has a Levenstein less equal function, which takes another parameter, which is the maximum edit distance. So it's an optimization. It just computes up to including this edits. Then it stops. And this actually helps a little bit. If you do this again with this function here, you save a little bit. Not much, but something. Okay, 50 milliseconds saved. Yeah, if you're Google, this means like $1 million a day or something. So, okay, still not good. Now, what else can we do? Well, there's trigrams. We already encountered them in the first part for the speed up of I-like. Trigrams can do the same trick, because you can say, well, I transform this into trigrams and the other word as well, and then I compare what is the overlap. How many trigrams overlap? I can also look at the sequence in this case, of course, and so on. So trigrams can be used. Actually, Postgres has 2 functions here. Well, no, an operator and a function. So I think this here is an error. You need to edit this out. So there is a function, similarity, and a matching operator that is the percentage. I misplaced this, which are things that use trigrams to give you a similarity between 0 and 1 between 2 strings. So 0 means they are identical, 1 means they are distant. I think the other way around. 1 is they are identical, and 0 is they are completely different, no trigrams in common. And they have this operator, which is just a easy way to say if the similarity must be larger than 0.3. So this gives you a Boolean back if the similarity is larger than 3. So this gives a very easy query where you can say, I want where word similarity operator query term. So you have a where clause. In the first query, we did not have a where clause. It needed to calculate Levenstein for all of these. And you can't index that because in Levenstein, the unknown input goes into the algorithms. So here, something else happens. Here, we created, I didn't say, but we did, here it is, we created our famous gene trigram operator, and this thing here can speed up this operator. So Postgres can very quickly, using an index, solve this where. And then everything you do in the select list is just computed on the hits. Okay, so this is fast. It's a completely different thing here. It's not the edit distance, but it's fast. And it also works. Wait a second, I already did the combined thing here, I think. Wait a second. I already, I skipped the thing. I need to do this one here. So, yeah, this it is. This is the query where I have this where. This where immediately finds, let's see how many. This immediately finds the 224 candidates and this is quick because there's the index, and then only on these it calls similarity or whatever you have in the select list. That's the trick. Always filter and then do the heavy start in the select list. So this already works nicely. It finds Postgres. Actually, it works really nicely because it finds also PostgreSQL in the second place, but this is not even wanted because if you say Postgre, the obvious misspelling would be Postgres. That it finds also Postgres is kind of sort of random here. Okay, this is very good. This is fast. This does it in 5 milliseconds. So we went from 160 to 120 with the optimization again to 6. This is something else though. People say, yeah, I don't want this because trigrams are strange. For example, trigrams don't work for very short things, of course. If you just, for example, for Mair, my name, my surname, it's hard. They won't get you that you misspelled it and there's no epsilon in it because it's just too short. It does not really work. So you need to have at least 2 or 3 or 4 trigrams. Otherwise, it does not make sense. But you can combine this. Nobody forbids to say, yeah, I want this for the fast where query, but the ordering or the where logic can then add also Levenstein. So, for example, you can do this and add Levenstein. This is what I did below here. Let me see which one this is. This should be this one, I guess. Okay. So here I show you the similarity, yes, and then I also show you the Levenstein. And this is still fast. Why is this fast? Because Levenstein is computed just on 200 and not on all of them. So you use the where to get less with trigrams, and then you still use Levenstein to get what you want. For example, you're interested here in this one, and you're not interested in Postgres because it's a 3. This might make sense. Now, okay, in this case it would even be correct, but normally you don't want PostgreSQL here. And you don't want Postgres XL because it's in other words, it's distant 3. So look what I do. I say here, and I want Levenstein to be smaller or equal to. Here we go. Then you get sort of what we already had before. But now it's fast because you use the trigrams as the first condition here in the where clause. I don't see the where clause here. Where? This one. So this makes it fast. And then this makes it correct in the sense of the edit distance. And Postgres sees there is a condition and condition. On the first condition, I have the index, I will use it. And then it will apply the second only on the one that survived the first. Postgres is smart enough to arrange this. So by trigrams, you can speed up indirectly Levenstein. Of course, this is not perfect because for very short things, the trigrams will just crash and not give meaningful results. That's everything. Now, people say, yeah, what about SoundX? What about all these algorithms? There is, Postgres has also all these algorithms that compare the similarity of words with the criteria that their pronunciation is similar. People use this for misspelled or misheard surnames. Postgres has all these, but the problem is they are quite centered on English. So maybe here, where we don't speak English, well, I do. I don't know why, because all of you understand German. But yeah, it's maybe not so ideal, because if you put Ohnewein or a Mair to SoundX, you don't get really good results. But they are there. If you want to use them, they are there. Okay, last part, semantic search. So this is a step up. 1, 2, and 3 all had as a basic lexical searching, pattern matching, if you want. where you look at the characters. Okay, so now we make a big jump. We want to do, the use case is we want to perform a search by meaning and not by string matching. That's semantic search. Now, I have here a little bit of an introduction. I can still manage. I want to give this because I think it's nice. This is also, people have crazy ideas about embeddings. They think it's kind of AI thing, but it's actually quite math still and quite surprising, but quite manageable in a way. So the idea is that embedding in this context means that you get a text, you feed it through something that does the embedding, and you get a vector as an output. If you don't know a lot about math, think about an arrow that points in some direction. A vector is just an arrow pointing in a direction. I have here a nice example. You could say, I do my own embedding. Let's play a game. I take a compass rose. That's a Windrose in German. I looked it up. I didn't know it's compass rose in English. And I say I want to take titles from novels, and I want to classify them in this Windrose. So in the way I want to do an embedding, I get the text of the novel with the content of not only the text of the meaning of the novel, and I put it in this Windrose. So let's just make up something. Normally this would be trained, but we make up something. We say fantasy and science fiction is north, mystery and crime is east, romance is south, historical fiction is west. Okay. Now you have Lord of the Rings that clearly points north. It's the archetype of fantasy. Now. What else I have? Sherlock Holmes is clearly east. It's a crime and mystery story. Romeo and Juliet is south. These are very clear examples. Where would you put Jane Austen's Pride and Prejudice? That's something that has a lot of historic stuff, so that would point it to west, but it's also a romance, so it would be south. Well, we can put it to southwest. Okay? If you go on and do this, you have kind of a long list with arrows, which are the novels that you embedded into a two-dimensional vector now. Now, somebody comes along and says, oh, I've read the biography of Bonnie and Clyde. What novels in your list are similar to this one? Okay, you could say, well, let's embed Bonnie and Clyde. Bonnie and Clyde is romance and crime, so that would point it to southeast. Okay, and now I can compute the distance because I say just take the degrees, the angle between these vectors. As easy as that. As Bonnie and Clyde points southeast, it will be 45 degrees away from Romeo and Juliet, which is south, and 45 away from Sherlock Holmes, which is east. It's very hard to not get confused by this. It's a bit closer, a bit more distant from Pride and Prejudice, because Pride and Prejudice is versus the historic thing, which is the other side, so it's 90 degrees. It's 45 plus 45 is 90. And it's very far away from Lord of the Rings. It's a whole 90 plus 45 away. Okay? Yeah, look, this sort of works. You can argue any way you want, but Bonnie and Clyde is certainly more related to Romeo and Juliet and Sherlock Holmes than it is to Lord of the Rings. So you kind of made your own primitive embedding where you can already rank texts by their meaning and not by what the strings are. Something as abstract as novel genres now maps into something that we can do computations on. We can compute similarities. We can rank them by similarity to others. So this is how embedding works. This is the whole thing. Now, if you think more about this, there are problems, of course. My Winters is way too simple because there might be a novel that combines science fiction fantasy with romance. So where you put that are opposite vectors. So maybe choosing these as opposite was not good. If you try to solve this, to make this better, you end up with the clear idea that you need more space. 2 dimensions is not enough to somehow describe these abstract meanings. You need a lot more space. We are thinking about high-dimensional space when we talk about embeddings. Typical numbers are incredibly large, 384 to 1024 dimensions, but this is not a hard bound. It can go even higher, but these are typically these are 384, 512, 768, always powers of 2, 1024. These are typical numbers. Now, this is incredibly vast. You can't imagine this. Think about adding a dimension to the plane. You get a room. You have lots of space more. It's way more complex. Now add 1 dimension. You have a 4-dimensional thing. It's really weird. If you add 100 of dimensions, it's completely out of scope. But this works. Of course, this is not built by a human that says, yeah, you point this here. But this is trained. So these are neural networks that are trained to put these texts into this vector space in a way that texts that are similar have close vectors and texts that are different are more distant. It's exactly the same technique for face recognition. Face recognition also maps your face in a vector, smaller vector. Typically they use 128 dimensions for that vector. And you train a model in such a way that 2 photos of the same face are closed and of a different face are distant. So you get what you want. Now, we don't have to do this because we get pre-trained models. Let's make a small skip here. This one here. So there are vast numbers of pre-trained neural network models that you can recycle. They are open weights. They come with the open source licenses. So, for example, there's a lot of with the MIT license, with the Apache 2 license. You can just use them. You have to find the good one for your use case. Here's a suggestion. This one is very good. PG M3. This is from Chinese people. And this is a multilingual model, so it takes texts from different languages and maps them to the same space, which is nice, because you can do language-independent stuff. But for this demo, I used a smaller one. I used PG small N version 1.5, which is way smaller, but it knows just English. And I choose a smaller one because I prepared this talk very late, and the larger model took too much time to. So I did it just with the English Wikipedia with a smaller model. And yeah, then you need software. So we have a model. We need software. How do we do the embedding? Well, there are extensions for Postgres that do the embeddings, that is, run this neural network and calculate the vectors from the text inside Postgres, but it does not make a lot of sense. The lingua franca in this space is Python, and this extension somehow, yeah, just embed Python in some background process. It does not make a lot of sense. So I suggest, if you want to do this, just stay outside Postgres and have your own program running. You can communicate, you can take the text, embed it, and feed the vector back. Just have to program the input and the output. It's, in the end, a little bit more work if you start, but you are not dependent on weird extensions that install weird background processes that you can't control. So I suggest you do this. I have a program here that does exactly that. Embed Py. Yeah, software. The software I recommend for this is sentence transformers, which is a famous Python package that is based on PyTorch that does this. Everybody uses this, so it's not just a secret recommendation. Actually, everybody does this. So, but this PGE thing is more of a little bit Sotobanco tip. So not everybody knows maybe that this is a very cool embedding model, but everybody uses sentence transformers. So take this with different weights. Okay, so I made this. You see, you call this sentence transformer here. This is hosted on Hugging Face. I connect with the database, and then I have basically what is just a loop that fetches the things from NWiki. I do it, by the way, with the titles. You could do it with the articles. You would need to use a larger model and probably implement chunking, so you have to cut the articles up a little bit because the longest ones are too long even for the larger model. But yeah, I had no time to do this, so I did it on the titles and with the small model. It's still quite meaningful. It's not that it does not show the power of this thing with a small model, but it works only for English. And I did it only for the title. Now, yeah, I read this and I do the embedding. This is just this call here. Everything is just some glue code. This one line is the call to do the embedding. And here I execute the insert back. There is some logic here to do it in a semi-efficient way. I take 1,000 texts and feed them in parallel through the model. So if you have a fat GPU, this will be very fast. I don't have a fat GPU, but it's still a little bit faster than doing one by one. And yeah, you wait 6 hours. And yeah, I did it with these 4 cores. No GPU, just the 4 cores. 6 hours it takes to embed 7.1 million titles into vectors that are, in this case, on the smaller side, 384 dimensions. I was talking about software. You need one thing. This is the first time here we use, we did use Postgres extensions, but just official extensions so far. For example, trigram is an official extension. This is the first time we need a third-party extension, which is the famous PG Vector. Here it is. This is a third-party extension that is distributed with in the official Postgres repository, so they are friends with the Postgres project. This is not an exotic thing that somehow a kid did yesterday. This is a established project in the Postgres ecosystem, so you can trust it. Yeah, this means that my embedding thing will feed this into these table embeddings that I created like this. It stores just the title because only the title is embedded, so no sense to copy also the article. And then it has this embedding, which is a type vector, which is the data type by PG Vector. And this is the dimension. So you need to do a 384 dimensional vectors because the small model wants that. The large model, I think, is, if I remember correctly, that's 768, if I remember correctly. So let's have a look. How does this look? Select star from embeddings, limit 1. I have to pivot this, otherwise it's not readable. You see, there is the idea, then there is the title, Alfred Weber, and then there's the vector. The vector is just 384 floats. These embed whatever the meaning of Alfred Weber is. Okay, so I don't know Alfred Weber, but maybe PG small knows, so there's some embedding in there. Now, for example, even if you don't know it, an embedding is certainly that this is a person. It's probably a German-speaking person. These are all meanings that you can infer just from this short text, and the model certainly knows these meanings. and embedded is in this vector. Now, yeah, we want to search. So, how do we search? The example is interesting places for sightseeing in the capital of France. This was also an example from my talk about PG vector some time ago. Yeah, let's just search for this. Can we search all the titles that are similar to this one? Well, we need to do this also from Python because we need to embed the question. Here it is. Here. Look, it's very simple. Modeling code, this one. F is the vector. That's basically all you need. Now, this vector is 384 floats. I could copy them into a query in Postgres, but it's not very handy. I do the query in Python as well. Here's the query. This is what it looks. Okay, so what do? I select the title, skip this a moment and go to the from. I select the title from embeddings, and here's the magic. I order them by this thing here. Embedding is the vector I saved, that I computed and saved in the PG vector column. This is the vector that Python will substitute. This is done in PsychoPG, which will substitute this place mark. This is like a parameter statement. What are they called? The SQL programmers there. The parameters. Huh? I'm missing the exact term. You don't concatenate things, but you put these placeholders. What's that called? No, I did not hear.
No, I call them placeholders.
Placeholders. Yeah, there's a name for this. I forgot.
They are in order.
Order placeholders. Like in Java, I think it's $1, $2. Okay. Okay, so this is the trick. You select from embeddings and you order by this thing here. What is this strange operator here? This is an operator that comes with a PG vector. This is the so-called cosine distance. This is a funny mathematical word to just describe a metric that gives you a number from -1 to 1, where I never remember. I think -1 is the opposite and 1 is the closest or something like that. It maps the degrees. In 2 dimensions, it would be 100 degrees. In the high dimensional space, degrees is a bit complicated to visualize to some easy number. So this is the distance. So I order it by distance ascending. The closest ones are top, and then the distance goes on. And I print here the same expression, but 1 minus the expression as the similarity. So 1 minus the distance is the similarity. Okay, let's do this. First one will be a little bit slower. Python query py. There's also always this line here. This is the model loading from the cache. So the sentence transformer prints this progress bar, but it makes no sense because it's loading from the cache, so it's actually quite quick. Oh no, it's already fast. Look, 5 milliseconds. Here we go. And this is the list of titles it got. Here you are. No, I skipped something. This is slow. This is still slow. I showed you the result with the index already made, but we are not there yet. Here's the explanation. This is still a little bit slow. It's already quite fast, actually, 1.6 seconds. It's not bad, but this is the version before the index, and you get this list here. So yeah, you see this is surprisingly well matching to what we asked it to look for. We asked it, what was the query? The query was, I don't see anything. Here, interesting places for sightseeing in the capital of France. That was the query, and we get these. These are not bad matches, I'd say. list of especially this one is perfect. List of tourist attractions in Paris. And as you can see here, the magic is that the words don't matter. I said in the capital of France, but it found the attractions in Paris. That's not a coincidence. It's not that it gives you attractions in Las Vegas. So it knows that this thing points to Paris, and my question also points to Paris, but the word Paris was not there. Yeah, that's it. Now, this is already quite fast, because this is already quite a well-optimized thing, this PG vector. But we can make this even faster. It's fast, right? Well, it is, but we can make it even faster. By now you know the drill. Postgres can index anything, but you need to know the secret index algorithm with the secret operator class, and this is kind of the inside knowledge. What we need here is, well, you can read the README from PG Vector. They tell you it's not that secret, but you have to read the README. Not everybody reads the README. The trick here is to use this index algorithm, which has the funny name of hierarchical navigable small world. It's actually called like this. And you need the vector cosine ops operator class, because you want to speed it up, this funny operator we use to compute the cosine distance. Now, the index is therefore done using this query. And I did this like just before the talk, okay? So I had to trick a little bit in this case. This thing you can do also on smaller machines, but it is a implementation that is way faster if it has at least the amount of memory that the index will be in the end. This index is quite large. It's 14 gigabyte. Okay, it's you say the title is small, but even if the text was long, it maps into 384 floats. Okay, so multiply 384 floats by 7 million, and you get something like 2 gigabytes, I think this is, if I did not miscalculate. No, then actually it's quite large. Wait a second, how much is, no, yeah, I have to multiply 2 gigabytes by 4, the size of the float. So 2 by 4 is 8, so we're getting closer. Huh? Of course, this is now a complete wrong calculation, but you get in this order of magnitude. And of course, the index must be at least as large as this one. Then you add the data structures, the pointers in the index, so it must be at least this size. And here, since I did this before the talk, I had to cheat. This is the only query in the whole thing I did on a larger computer. I scaled up the computer momentarily and gave 26 gigabyte of maintenance work mem. I estimated this would be enough. And then it could do it in 18 minutes. Otherwise, on the machine with 16 gigabyte, you can do it, but it prints a warning in the Postgres log that I don't have enough maintenance work mem. I will do the job, but it will take you a long time. And this is not just twice or 5 times slow. This is like 50 times slower if you don't have enough RAM. So this index has certainly the problem that it's slow to build if you don't have enough RAM. If you have enough RAM, it's okay-ish. But it's the fastest thing you can possibly get. This is a really, really, really cool algorithm that gives you incredibly fast performance here. And here you get these 5 milliseconds that I already demonstrated here, but there are 2 additional informations we must add here. And now I'm almost finished. One information is that this is working because you say, how is it possible that it compares all these vectors in 5 milliseconds? It can't do that. It can't calculate 7 million distances in 5 milliseconds. That would be not possible. what the trick here is that the when Postgres sees this order by, it directly calls into this implementation here and gives the whole order by this one limit 10 to the algorithm. And the algorithm does a top-end search. It does not compare everything. It knows the vector, it needs to look for similar vectors and looks around here. Okay, so it does not compute the distance for 7. That's why it's so fast. But it's only working if everything falls into place. So you really have to formulate it. You really have to have the index that uses the right operator class. And you need it to formulate exactly this way. You can't leave out the limit and store it in a temporary table and then select from the temporary, because then the information is lost and will be way slower. You have to do it exactly like this, and then it's super fast. Second point is this is approximate. If you pay attention, these are not exactly the same numbers. They are an approximation. And the first things here are identical, but if you compare, starting from this one here, I think, they're also different. The ordering changes a little bit. So this is an approximate algorithm. It's incredibly fast, but approximative. I still recommend this, because you say, no, I want to do exact calculation. It makes no sense, because also the model is approximative. We're talking about meaning here. You don't know on what this thing was trained by the Chinese. It's always a kind of a sort of fussy thing you're doing here. So it makes no sense that you want this to the 4th decimal digit exactly calculated. So I think it's a very good trade-off between super speed and approximation. This works really well. Give me a query. I'm almost, don't worry, we can go to the Schnittchen.
What if you use South Tyrol instead of France in this query?
Okay. Interesting place for sightseeing in South, yeah, well, this is of course a piece of cake. South Tyrol. Okay, first hit South Tyrol. Holidays in Tyrol. South Tyrol, Museum of Archaeology, list of castles in South Tyrol. Perfect. It works. Semantic search with embedding vectors is really magic. Here again you see this. This is a large index, 14 gigabyte. This is a little bit on the boundary of what this machine can do. If you do it now, of course, if I repeat it, it will be super fast. The slow startup here is Python that needs to load the model. That is the slowness. The time it takes the query is actually this time here, right? So this is fast. If you go on, eventually you probably will, it depends on what the machine is doing. If the machine is doing a lot of stuff, it will forget parts of these 14 gigabytes and then it will be a little slow again. This is probably on the border with this 16 gigabyte, but it works. Give me something more complicated.
But if you write nonsense,
Yeah, tell me nonsense.
yeah, it's the same, but ketchup times 7. The capital of ketchup. Ketchup,
The thing you eat. How do you spell? Now this is how do you spell ketchup in English?
This is right. So interesting basis for slicing in the capital of ketchup.
Will probably tell you something about sightseeing, I guess. Place it to, yeah. You see, it's quite clever. It's quite clever. It says I don't know what this guy wants to visit, so places to visit. It's actually the best possible answer it could give. And then, as Rudi said, yeah, list of food and drink monuments. Okay, the guy wants to visit something, and ketchup is a food, so yeah, list of food monuments. It works. It's fast and it works. Okay, to finish, few notes here. I don't think this is really important. You can do larger text. You can match the whole article, but don't go over 10,000 characters. Depends a little bit on the text. Because if think about a situation where you have a large model that can, well, the model does not need to be large, but you need to have enough space for embedding large text. It does not make sense because a large text, a whole book, talks about a lot of concepts. So the meaning is not a clear direction. You always want to have a text that is somehow talking about one thing, an abstract or at most an article of 10,000 charts or something like that, but not huge text, because then it starts to not making any sense anymore. And what else? Embeddings is a general concept. You can embed images. Clip is a very cool model that embeds images and texts into the same vector space. So you can use text to search images. You can give it images to search text or other images. You can do any combination. And finally, this is also quite popular nowadays. The keywords is hybrid search. You do full text search and semantic search, and then you just combine the two ranks. Okay? So if you find a document that ranks up in both, give this as the first result. You can just do an average ranking, or there are different algorithms to do this, to combine two ranks. Nobody forbids to just do both. Okay, yeah, that finishes. I think I showed you all kinds of examples of searches and the fact that Postgres can do them all in milliseconds. And time for questions. Or for example, if you want to search something in Wikipedia, we're here.
Shall we search which is the sense of the life?
Okay. How do you want to search it with full text or with semantic search? Both. Let's do both. Okay, so the difference is that now here full text is on everything, title plus article, and semantic search is only on the title. But it could be either way. Huh? It's not a limit of the technique. It's just my example here. So what is the meaning of, is life in this case with F spelled?
I think so.
What is the meaning of life? So this is the semantic one. Well, there is obviously a Wikipedia page about meaning of life. So yeah, this was easier than you thought. It does not have to answer. It's not an LLM, so it does not need to answer. It wants to find Wikipedia titles, so it did. And now we will use this also for full text. So let's copy one of the full text queries here. Let's pick the South Tyrol query. Where it is? This one. And here we will, these are keywords, so we'll say meaning. We could, there is also an operator I did not tell you, close to, but not following, but yeah, let's just say meaning and life. Yeah, do it like this. Now it started to cache in the cache from the embeddings. So the cache, the index from the full text search is now cached out, and it needs to. There is a, if you would look with I/O top, you would see a lot of I/O now because it's again loading the other cache. The semantic index is 14 gigabytes, so that populated most of the machine right now. Oh, we forgot to do the ranking. Sorry. Does not make sense. This is of course a query that gives you very lots of results. Look, 175 results, because meaning and life is common words. We need to rank them, otherwise we don't get anything. And so I forgot to copy the rank stuff, which is I can take from, help me find it. Where's the ranking thing? Lower, yeah, it's lower. We look for ts rank cd. That's the function. Here, ts rank cd. Here it is. Okay. Now, this is already a lot of results, 100,000 results. So this is already a thing that you should probably not compute. Now I want the one where is it just once. The ranking for, because 100,000 is already too many results to compute the ranking for in milliseconds. We can do it, it will just take seconds. But for a production system, 100,000 is too much already. Meaning and live. And this is now not slow because it's not in cache. It is in cache now. This is slow bit because it needs to rank all those 170,000 documents, which you should not do. This will likely also find these same things as the other one. But in this case, it will be slower because the other one does not need to rank. Think about it. The other one does not need to rank because HNSW will find the top n already. And here, I could do a limit 10. You say, yeah, here you didn't do a limit 10. No, if you do a limit 10 here, it does not matter anything because it still needs to compute the rankings on all of them. Because there's the order by R. So it still needs to compute 170,000 rankings. That's also one reason why the tendency is now to go towards semantic search, because ranking is somehow easier there. Okay, yeah, see the first hit is, this is now large because there's probably one title that is very long, so it gets a bit stretched. But you see it's basically the same thing. Meaning of life is also the first hit. So both ways gave the best first hit, I'd say. Okay. By the way, there's a difference, of course. This one is looking at the whole article. The other one was looking just at the title. So to be fair, we also have to say that.
If you compare with the search results of Wikipedia, the list of the
Well, I don't know if they do semantic search. So I don't know what they give you if I say this. I have no idea how they do search. I looked a little bit and I have the suspect that they optimize it to avoid ranking long lists, as I said. But I don't know how they do it. So let's go to wikipedia.org. I'm typing blind because I don't see anything. No, I don't think they do semantic search, so they have probably sort of no idea what is happening. They probably do full text search, and they highlighted it as well. They probably picked up a few words and did a full text search on the words. So they obviously don't do semantic searching here. Very good. Thanks for the patience.
networking and enjoying the drinks. A brief and short update about the upcoming events. Next Software Developer Thursday will be on June, and Abdullah will present a prototype of Richie Mini. We did internally to answer questions about the makerspace, a laboratory here at Neutech Park, using Steward. Thanks also to the collaboration with Chris, we were able to integrate Steward and Richie Mini to answer and having a complete digital sovereign bot that answer questions about the laboratory here at Neutech Park. There are still 3 days available for talk. So if you have something you would like to share with the community, drop me an email and I will be happy to find a date for you. And last but not the least, next Friday, 15 May, there will be the Open Data Hub Day, a full day dedicated to the topic of the Open Data Hub, Open Data and data spaces. If you are interested, just go on opendatahub.com and you will see the entire program, which includes 2 tracks, one more business and one more technical. I hope to see you there. Thank you all for coming and hope to see you in the next events. Bye-bye.